We now want to look at the concept of solubility. The solubility product constant for the equilibrium between barium sulfate and the ions that it forms, barium 2 plus aqueous plus sulfate SO4 2 minus aqueous, is given by a constant called the KSP. It's defined as the concentration of the barium ion times the concentration of the sulfate ion. Notice that there is no denominator like a typical equilibrium constant. The KSP is also generally a very small number. In this case it's 1.1 times 10 to the minus 10th. In general, the KSP expression follows the following rules. Lead chloride is in equilibrium with lead ion and 2 chloride ions. The KSP would be lead, the concentration of the lead ion, times the concentration of chloride ion. Notice that it's squared. The coefficient becomes superscripts in the KSP expression. This is a table of solubility product constants for some slightly soluble ionic compounds. Again, notice that the numbers are very, very small. What's the solubility of silver chloride in grams per liter? The equilibrium is silver chloride in equilibrium with silver ion and chloride ion. KSP is given as 1.6 times 10 to the minus 10th. Again, we do the ice table. The initial concentration of silver and chloride ion is 0. The change we're going to call plus S. And at equilibrium, the concentrations will be signified by S. So the KSP is equal to the concentration of the silver ion times the chloride ion. That equals S squared. S then will be equal to the square root of the KSP, or 1.3 times 10 to the minus 5. The units are moles per liter. The silver ion then is 1.3 times 10 to the minus 5 molar, and the chloride ion is 1.3 times 10 to the minus 5 molar. The solubility of silver chloride then is 1.3 times 10 to the minus 5 moles of silver chloride per liter of solution. If we multiply it times the molar mass of silver chloride, 143.35, our answer is 1.9 times 10 to the minus 3 grams per liter. This is a table showing the relationship between KSP and molar solubility for different cases. Again, notice that the coefficients become exponents and make the KSP expressions a little more complex. Can we predict precipitation? Consider this. Calcium phosphate in equilibrium with calcium ion and phosphate ion. We establish a quotient Q as the calcium ion concentration initially squared times the phosphate ion concentration cubed. If Q is less than the KSP, no precipitate will form. If it's equal to the KSP, then you're at equilibrium. But if it exceeds the KSP, a precipitate will form. Here's an example. If 2 milliliters of 0.2 molar sodium hydroxide are added to 1 liter of 10th molar calcium chloride, will a precipitate form? The ions present are sodium ion, hydroxide ion, calcium ion, and chloride ion. The only possible precipitate is calcium hydroxide according to the solubility rules. If you've forgotten the solubility rules, please review them. Is Q greater than KSP? That will answer the question of whether a precipitate will form or not. So the initial concentration of calcium ion is a 10th molar. The concentration of hydroxide ion is 4 times 10 to the minus 4 molar. The product of the two is calcium ion concentration 0.1 times hydroxide ion concentration of 4 times 10 to the minus 4 squared, or 1.6 times 10 to the minus 8th. The KSP for the calcium hydroxide is 8 times 10 to the minus 16. The Q is less than the KSP, so no precipitate will form. The common ion effect in solubility. The presence of a common ion decreases the solubility of the salt. What is the molar solubility of silver bromide in pure water and in 0.0010 molar sodium bromide? The equilibrium is between silver bromide, silver ion, and bromide ion. KSP 7.7 times 10 to the minus 13. S squared equals the KSP, so the S is equal to 8.8 times 10 to the minus 7. If we add the sodium bromide, we get a common ion. We get sodium ion and bromide ion. The bromide ion is 0.0010. Again, the same equilibrium. The shift will be towards the silver bromide. It'll decrease the solubility of the silver bromide. So the silver ion is going to be represented by S, but the bromide ion is going to be 0.001 plus S, which we can approximate as 001. Remember that the S was 8.8 times 10 to the minus 7, which is much, much less than 0.001. So the KSP now is 0.001 times S, so S is now 7.7 times 10 to the minus 10th, which is much less than the original.